start. Could you start now?
Okay, hi. Today I will talk to you about our recent work about obscured and Compton-thick AGN. Just to remind you that obscured AGN are AGN that we cannot directly see the central emission. And in terms of optical and UV radiation, the obscuring material is the torus itself. But for X-rays, it can be the broadline region, the torus, and the multiple observer systems in between. So just based on the X-ray obscuration measured by the hydrogen column density, we classify these systems as unobscured and obscured and Compton-thick AGN. And these galaxies are important for our understanding of AGN and galaxy evolution and galaxy formation and evolution, and accretion history of the black holes seen from the X-ray background radiation. And the number of these systems is important too for our understanding. So that's why we would like to have new techniques and new information to find these galaxies. And one wavelength is the hard X-rays, because they're not obscured in hard X-rays, and the other wavelength is the infrared, because they have very strong infrared radiation, which is not obscured. Then we selected some AGN from the BAT Swift catalog. So BAT scans the whole sky in this hard X-ray range. And from this catalog, we selected non-beamed AGN, and we cross-correlated with Akari Bright Source Catalog version 2. And this is our main sample. Then we wanted to have the NH measurements and the redshift measurements. Then we are left with 338 sources. And by using the NH measurements, we just classified them as unobscured, obscured, and Compton-thick AGN. So this is a local sample. So the median redshift is 0.02. Then to study the spectral energy distributions, we collected data from UV to far infrared. We used GALEX, SDSS, 2MASS, WISE, Akari, and Herschel. So here, Akari data is the main point, the main data that we would like to have, because the dust SED has a peak around 100 micron. And when you have the Akari bands at 90 and longer than 100, like 140 and 160, then you can have a better constraint for the dust SED. But unfortunately for our sample, the detection rate at Akari 140 and 160 was low. That's why we wanted to use Herschel data when we have it. Yes, but when we combine data from different telescopes, we need to take into account aperture corrections. And for our sample, especially, they are nearby sources. So that's why we use the beam corrections given by Clements et al. 2019 to our Akari 65 and 90 micron. Then for comparison with Herschel data, when we compare data, we see that there are some outliers here, but there's a good agreement. And we find this median difference for our sample. So we just add this difference to uncertainties. And for 160 band, we did the same thing. We add this difference to our uncertainties. Yes, for the SCD, so we want, since CIGALE works with the energy conservation principle, we wanted to have at least one detection at each wavelength region. So that's why we ended with 158 final SED fitting sample. So this is just an example of one source that that we see in green here is the AGN component. We use the AGN model of Fritz et al. 2006. Then here the red one is the dust emission, and the black one is the total best fitting model. So when we have this best fitting model for each of our source, then we divided our sample into unobscured, obscured, and Compton-thick AGN, and we wanted to have the average SEDs of each population. So each green one is the best fitting AGN model from CIGALE, and here the black ones is the average SED of each subsample. So then we overplotted all these three mean SEDs here together to see the similarities and the differences. So in the optical UV part here, we see that the Compton-thick and obscured AGN are dominated by the stellar emission, but here the unobscured ones, of course, have this excess from the AGN emission itself. So this is consistent with our understanding of AGN and our model. So these SEDs are normalized at 1 micron, and here near like 10 micron, maybe I can say that the unobscured AGN has a slightly stronger continuum, and within the between the 1 and 20 micron range, we don't see much difference. For Compton-thick AGN, here we see that far infrared bump is stronger here. So far infrared bump is coming from the dust SED, dust in coal dust in the galaxy. So this might suggest that the two can be related, or the dust from the host galaxy can have an effect on the AGN obscuration too. So later we checked, since we have these different components from our SED fitting, we checked the luminosity relations between dust luminosity and X-ray luminosity, AGN luminosity and X-ray luminosity, and total infrared luminosity and X-ray luminosity. Here we see strong correlations, and we also quantified each of these relationships. Then we also checked the infrared colors. So we wanted to see if infrared colors depends on the NH. But we checked many different color combinations, and most of the time we couldn't see a clear color distribution. But in this particular color diagram, here in this axis here, in this range here, above 2 and below 2.7, we realized that we have only like 4 Compton-thick AGN in this region. This is just an experiment by eye. So then we said, okay, can we understand this? So in terms of mid-infrared and far-infrared color here in this axis, these blue contours are Akari infrared galaxies from our previous work. So we see this difference because this color mainly compares the AGN torus and the far-infrared dust. So we expect to have AGN blue colors here. So we understand this part. And here, when we look at the spectral infrared spectrum of one of these sources here, as I show you, we see that these systems, of course, have deep silicate absorption. So this Akari 9 micron band shows us this absorption here. So when we have a deep absorption and a steep continuum, we see a difference in colors of these Compton-thick AGN. Then we wanted to test this color selection in our large Akari galaxy catalog. Then we find 3 candidates that I show here with the science symbols. And one of them was an unobscured AGN. One of them is a highly debated source that its nature is kind of not agreed well. But one of them is NGC 4418, which is a known Compton-thick AGN. Then again, by just experiment, we said maybe we should push this limit upper to only select Compton-thick AGN. So we decided just this number. But we ran out of Akari infrared galaxy catalog. So we just made an Akari and WISE large Akari catalog without any restrictions of nature of these sources. Then we found like 300 candidates here, as I showed, like the gray dots. And again, one of them was a galaxy, and it was again a non-Compton-thick AGN. And most of the other sources are galactic sources like planetary nebula or H2 regions. But this is, I'm still working on these nature of these sources. I have still some candidates. But at the very least, what we learned from this study is that mid-infrared photometric bands covering like silicate absorption and mid-infrared continuum can be used as a NEP tool to select this really heavily obscured AGN. Yeah, I think that's all from me.
Okay.
Thank you.
Thank you very much. Okay, first of all, I got a question from Matt on Slack. Why do you think the Akari fluxes are lower than PAX? You said that's aperture mismatch, but perhaps you could explain further. Ece, can you add something about that point?
Yeah, for Akari here, yes. Actually, here it was, yeah, Akari has a large aperture, and here the Herschel measurements were done with another study that they used. They used this different kind of apertures for each galaxy in the bad sample. So that's why we trusted their measurements more here. Yeah, so I mean, for Akari it's a fixed large aperture, but for their study they have the apertures for each source here.
Thank you very much. We have another question on Slack. First one is from Jinting. Could you comment on the average stellar mass of different AGN populations and if they would affect the average SED?
Just can you repeat again?
Okay. Could you comment on the average stellar mass of different AGN populations and if they would affect the average SED?
Stellar mass?
Yeah. For different populations.
Okay. Actually, here, since we didn't have, the optical homogeneous data set in the optical UV part, actually, I didn't check the stellar masses from CIGALE here. Our main interest was in the far infrared part and the AGN itself. So that's why, I mean, I didn't see, I didn't check it.
Okay, we have one more quick question on Slack from Tomo. What is the plan to confirm D300 candidates? Do you use Newster or Elo jitter? Any idea?
Yeah, for these candidates, like I would say, like really most of them are galactic sources, but most of like the ones that are classified as an infrared source in the databases, they don't have X-ray data in the archives. But I'm still working on them, and I will let Tomo know.
All right, so I think time is almost up. So thank you very much.